So, during my last two classes, I have discussed how we can determine the deflection of a lateral loaded pile by considering pile as a finite beam and pile as a semi infinite beam. But in both the cases, it was assumed that kh value or the horizontal subgrade modulus value is uniform along the depth of the pile. So, that is suitable for if the soil is cohesive soil, but if the soil is granular soil, then this kh value changes linearly with depth. So, in the today's class, I will discuss how we can determine the deflection of a lateral loaded pile if this kh value changes linearly with depth. Okay. So, now, here that is the concept which is proposed by Rees and Matlock 1956 and then 61 it is modified. So, the piles are supported by linear spring with varying kh with depth. Okay. So, now here the kh is taken as eta h and z divided by d, where z is at any depth, d is the diameter of the pile, and where this eta h is equal to coefficient of subgrade reaction. Okay, and whose unit is also kilonewton per meter square per meter, or sometime it is called unit subgrade modulus or unit modulus subgrade reaction, coefficient of subgrade reaction or coefficient of modulus of subgrade reaction. Okay, or sometime it is called unit subgrade reaction or subgrade modulus. Okay. So, now, that means, here we can say that kh is equal to kh for clay soil, that means uniform, and for the granular soil we can use this concept. Okay. We can use this one. Okay. So, now this approach is valid for long pile, can be applicable can be applied or can be applicable for long pile or can be applied for long pile, applicable or applied. Applied for the long pile. So, how we can say the pile is a long pile? If Z max is greater than 0. What is Z max? Z max is equal to L by T. So, sometime it is called greater than 4 or greater than 5 also. So, that means, if Z max, I will recommend if Z max is greater than 4, you can use this approach, and Z max is L by T, where L is the length of the pile and T, which is called is the relative stiffness factor can be determined as fifth root of EP IP divided by eta h. Okay. So, as I mentioned, eta h is coefficient of modulus of subgrade reaction, or it is sometimes called unit modulus of subgrade reaction. Okay. Now, for the free head pile, the expressions are given that for the deflection can be calculated as h t cube divided by E p I p a y plus m 0 t square E p I p into b y. So, a y b y are the coefficients. Okay, so, these coefficient can be obtained by basic differential equation, by solving the basic differential equation for the beam on elastic foundation. Okay, so, that means here again this pile is model as a beam and which is resting on the spring. So, this beam which is resting on the spring, that means beams on elastic foundation. So, that equation can be solved by finite difference technique. So, I have discussed that how you can solve the beams on elastic foundation, those equations by finite difference technique, and after solving that you will get these coefficients. Okay. So, that means this h is the load which is acting, and here it is the moment, because here there is no, here h and m both are acting at the same direction. That means, this moment is not due to the fixity. Okay. So, this is the external moment which is acting. Okay. So, that means, here we have to add the deflection due to this h and due to this moment. So, that is added here. But remember that in the previous case, when we solved the pile as a finite beam, we applied h and moment in opposite direction. So, that means, here h and moment both are applied due to because the moment is applied due to the fixity of the fixant. Okay. But if the moment and h both are applied in the same direction, that can be also solved. Okay, by using that equation. In that case, you have to add the deformation due to the moment and due to the horizontal force. Okay. But here that is applied here due to the moment and due to the horizontal force. So, that means, here the total deformation will be something like that, and this deformation is y, which is the summation of the contribution due to h and contribution due to m. Okay. So, now the theta expression is h t a m plus m 0 b m. Then the shear force, or sorry, bending moment is given, or sorry, these equations, this is the moment one is given with theta. With theta, the expression is h t square divided by E p I p, then a theta plus m 0 t E p I p b theta. Okay, b theta, or here the table is given for b s. So, that is why I am giving b s, s for slope. Okay, because these values will be given in tabular form. That is why I am writing the same, I am giving the same notation. So, this is h t square E p I p a s t cube t square. Okay. So, m, this is moment is h t a m plus m 0 b m. Shear force, it is h AV plus M0 divided by T BV. Then the reaction, okay. This is small q is H divided by T AP plus M0 T square BP. So, these equations are valid for free headed piles and the coefficient will be determined by this table. So, this table is given for different z value, this is given. So, here this is the capital Z, which is basically the small z divided by t. Okay. So, small z divided by the t. So, this is these equations are given, these coefficient we can determine for different small z, z is the so here this z is at any depth. Okay. So, z is at any depth, we can determine these coefficients. So, this is AY, AS, M, AM, AV, AP, then BY, BS, BM, BV, BP. So, all these coefficient can be determined for at any z value. Okay. So, and then these equations are valid for a free headed pile. So, what will happen if it is a fixed headed pile? So, for the fixed headed pile, so I can write here for fixed headed pile. So, again there will be a moment will be developed due to the fixity and that moment is equal to M0 and it is given that it is will be developed is minus 0.93 Ht. So, this moment will be developed due to the fixity and that means this is moment due to fixity. Okay. So, that means for fixed headed pile a moment will be generated due to the fixity is minus 0.93 Ht, H is the horizontal load which is acting. So, now let us solve one problem and we will see that how we can determine the deformation for a pile where kh is varying with depth. So, again the same problem I am taking, that determine the deflection at ground surface, that means z will be equal to 0 for pile with d is equal to 0.4 meter and L is equal to 10 meter, because it is applicable for the long pile and H is 50 kilonewton, which is applied at the ground surface. So, EP IP is 37 into 10 to the power 3 kilonewton meter square. Then eta H, then eta H is 5000 kilonewton per meter square per meter. Okay. Because for the soft clay also these variation can be observed for very soft clay and the granular soil. Now, water table is at ground level. Okay, so that value is not required for this particular approach, but anyhow that information is given what a table is at the ground surface. So, first we will check whether this approach we can be used or not. So, first we will take t value which is fifth root of EPIP divided by eta h, then fifth root of EPIP is 37 into 10 to the power 3, then this is 5000. So, this will be 1.5 meter. Okay. So, this is 1.5 meter. Now, L by T which is 10 divided by 1.5. So, which is 6.67 which is greater than 4. So, we can apply this theory, because we can apply this theory. So, now the deflection for free headed pile so free headed pile this deflection is h t cube divided by EP IP into A y at z equal to 0. Surface we have to determine, and we are not taking the moment contribution, because moment is not applied here. So, that will be equal to h is 50, t is 1.5 square cube. So, 1.5 cube divided by EPIP is 37 into 10 to the power 3, then AY at z equal to 0. So, what is AY at z equal to 0? So, AY at z equal to 0 is 2.435. So, we will write 2.435. Okay, because we are calculating the deflection. If you want to calculate the moment, then you have to take the AM, okay, at z equal to 0, which is equal to 0, because it is a free end condition. Now, this is equal to 11.11 millimeter. Okay. Now, for fixed head pile or fixed headed pile, so we have to determine what would be the moment developed due to the fixity, that is 0.93 h t, okay, similar to the previous concept. So, this is 0.93 into h is 50 into 1.5. So, this is equal to minus 69.75 kilonewton meter. So, moment due to this deflection due to this moment is equal to, now you will take the contribution due to the moment, this contribution, and that we are putting as a minus sign, because now moment is minus. So, this will be m 0 t square divided by E p I p, then B u I at z equal to 0. So, what is B u I at z? Because this is the moment contribution, because now in second case when pile is a fixed pile, we are considering this moment deflection due to this moment, and that time again. So, that time the free headed deflection you will consider, but you have to subtract this deflection due to this moment m 0, which is developed due to the fixity of the pile. So, that means here B u I is how much? B u I is 1.023 at z equal to 0. So, you will write minus 69.75, then 1.5 whole square, EPIP is 37 into 10 to the power 3, and BUI is 1.023. This is 1.023. Okay. So, 1.023. So, that is equal to minus 4.34 millimeter. So, the net deflection will be 11.11 minus 4.34. So, that will be 6.77 millimeter. So, for the fixed headed pile, deformation at the head is the is 6.77 millimeter, but for the free headed pile that deformation is 11.11. Okay. So, that means for the fixed head there will be deformation, but the slope will be 0, and free head there will be definitely a deformation and the slope will be also there. So, this is the settlement for both the cases I have discussed, when the your KH is uniform and with varying KH. But all the cases I have discussed that your for the single pile. So, then for the group pile, how we can determine this deformation or the deflection. For the your for pile under compressive load, I have discussed the how you can determine the deflection for a pile group in clay specifically. So, here also I am giving one idea that by using the elastic approach, you can determine the deflection of a pile group under lateral load also. So, how you can do that? Suppose you have a pile group of say four piles, or you can say there is a one case is 4 pile. So, another case is say a 9 pile. Okay. So, this is a pile group, and you are suppose in first case this is the pile group whose diameter is 0.3 meter and spacing between the pile is say 1 meter. Okay. So, now I want to determine the deflection of this pile group, where the lateral load is applied in this group is 500 kilonewton. A 500 kilonewton lateral load is applied in this pile group. So, in this pile group we have to identify the similar type of pile. So, here all the piles will be similar type of pile. Okay. But for this group all the piles will not be similar type of pile. For example, this will be similar pile, this will be similar type of pile. Okay. Suppose if I name these piles, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So, this 1, 3, 7, 8, 1, 3, 7, 8 are in one group, say A group, because these are similar type of pile 1, 3, 7, 8. Similarly, 2, 4, 6, 7, this will be 7, 9, 1, 3, 7, 9, yeah. Then this is 2, 4, 6, 8, they will be in another group. Okay. These will be a similar type of pile, and 5 will be one particular group, single pile, because that is a single. So, no other pile will be similar to this fifth pile. So, for this type of group 9 pile group, so these are the you have to make a group of similar types of pile, and but here all 1, 2, 3, 4 are in one group, because they all are same type of piles. So, suppose I am solving this type of problem. So, first case, this is the problem where every pile is taking the similar amount of horizontal load, and that is H 1, say H 1 will be 500 divided by 5. So, that will be 100 kilo 500 divided by 4. So, we are this is 4. So, this will be 125 kilonewton. So, a single each pile is taking a load of 125 kilonewton, And then here the equation is that we are taking the deformation of a pile group of a pile group. Suppose if we know the deformation of a single pile, and if I take that deformation for a single pile, that is fine. For that deformation will be there for a single pile, but there will be the effect of other piles on a particular piles in the deformation. That means, there will be a interaction between the piles, and because of that interaction the deformation of a particular pile will change or will increase. That means, here the reason is that deformation of one pile, where that will be the deformation of the one pile itself plus the deformation due to the other piles. That means, the deformation of the one pile will be the deformation of that pile plus the deformation of the pile deformation due to the effect of pile 4, due to the effect of pile 3, due to the effect of pile 2. So, that will be there. So, that is why I can write the deformation of that particular group will be the deformation of that pile into the load which is acting on that pile plus same acting load is acting on the other piles also, this is H 1 plus the interaction factor. So, this is this interaction between 1 to 3 or 1 to 2 plus the interaction between 1 to 3 plus the interaction between 1 to 4. Why 1 is taken? Because all the piles will behave similar way, because they are in same group. In case of 9 pile, 3 cross 3 pile, there will be 3 such piles group. Okay? But here there is one pile group. That means, what we have taken? We have taken the deformation due to that pile itself. So, here the interaction factor value is equal to 1, because it is that pile itself. Then the interaction factor for other piles. So, these are called interaction factor. And these interaction factors are the function of diameter and spacing between the pile. So, this is spacing, say this is the diameter. So, this is function of diameter, spacing, the angle between the direction of horizontal load. Suppose this is the direction of the horizontal load. So, here this angle is how much, here this angle is changing, here this angle is changing. So, here it is 0 degree, then it is 90 degree, then it is 45 degree. So, this angle of the direction of the pile with respect to the direction of the load. Okay. So, that angle, it is function of that angle. Okay. So, now it is function of the Poisson ratio of the soil, function of the length by diameter, then it is function of the stiffness Kr, okay, which is Kr is equal to Ep Ip Es L to the power 4, where L is equal to length of the pile. So, that means, this is function of diameter and spacing, function of the angle, function of angle means angle with respect to the direction of the load, or angle of that particular pile with respect to the direction of the load. It is function of Poisson ratio of the soil, it is function of length and diameter of the soil, then it is function of Kr. Kr is basically the stiffness of the pile. So, that means, Ep, Ip, Es. So, all these things are involved for interaction factor, and these interaction factor values are given in tabular form for different cases in the book that Paulus and Davis. So, you can get those values from that book for different cases. I am just explaining what is the concept of using that interaction factor, where you will get the chart under different condition. You should know the angle, you should know the Poisson ratio, then length by diameter, then diameter and spacing and Kr value. So, if you know all these values, based on that you will get the interaction factor. So, you will put those interaction factor, then you will get this deformation. For example, in this particular case, this is rho A by rho 1. So, I can write H 1 is how much? Is 125, H 1 is 125. So, this will be 1 and 1 1 2. So, this is given is 0.48, then this is alpha 1 3 is 0.34 plus 1 4 is 0.35. So, these are the values, and then finally, I will get this is 271.25. So, rho A will be for the group, because if it is a rigid pile cap, then we will assume that all the pile will deform by same amount if the piles are with rigid cap. So, this will be rho 1 into 271.25. Rho 1 is basically the single pile deflection, and that is given as a 0.032 millimeter per kilonewton. That means, it is for per kilonewton, it is 0.025 millimeter, and generally it is given as such as that 4 millimeter for 125 kilonewton of load. So, you can get it for per kilonewton, and then now you can determine that rho 1 is given, this is also in terms of kilonewton, this is in non-dimensional parameter. So, if I multiply with 0.032 into 271.25, it is per kilonewton, then the deformation will be equal to 8.68 millimeter for this group. So, that means, for the single pile deformation was say 125 kilonewton, 4 millimeter for 125 kilonewton. So, that you have to convert it to for millimeter per kilonewton, then we multiply that. So, this particular group, this 4 pile with this spacing, this diameter, the settlement of the group will be 8.68 millimeter, whereas single pile settlement was 4 millimeter for 125 kilonewton of load. So, this interaction factor values you can get from those book, those charts are available. So, I am not giving here all those charts here, it is only the concept I have discussed. So, charts, those value you can get from that book, and then you can put this value here, and you will get the deformation for particular group of the pile. So, that means here, so and how you will get the single pile deformation? You can get it by elastic analysis also, this single pile deformation you can get it, and I have already discussed that how you can get the single pile deformation for this using these two concept. One is with varying KH, another is uniform KH, or by pile load test also under lateral load you can get the deformation of the single pile. So, once you get the single pile by using this approach, you can get the deformation of a group pile, and for the pile under compressive load, deformation of a group pile I have already discussed. Okay. So, this way I am finishing today's class. So, next class I will discuss that how you can develop a generalized PY curve for a pile under lateral load. Thank you.